Welcome to the first day of summer general physics. In this sixth video, we'll be looking at coordinate systems and then the physics concepts of path length and speed. Coordinate systems are very important when you're trying to describe the position of something or how it is moving. Directions and positions of all events and objects are specified by a coordinate system. A coordinate system consists of an origin plus a set of coordinate or axes. So for example, if you wanted to describe the location of a certain building on campus, you might say, you start at the campus center and then you walk 50 feet north and 200 feet west. The origin would be where you start, where everything references. That would be the origin, in this case the campus center. Then east, north, south, east, west, those would be your axes. That would be how you would specify the location of an object. We do the same thing in physics whenever we have a problem that involves locations and motions. We have to specify where are we measuring these positions from, and then also some axes that tell us something about the directions. Now the choice of the coordinate system is totally up to the problem solver. This is something that you choose, and you can choose a system that simplifies your problem. So for example, many problems will be solved using a Cartesian coordinate system, where you have an x and a y axes, and objects are at locations specified by x and y coordinates. Now later on in this semester, we'll be looking at rotating objects. And for rotating objects, a useful coordinate system is one where we have some sort of reference line, and then the positions of things are given as a distance from the origin as well as an angle from that reference line. So for example, if you were looking at a wheel, all points on the edge of the wheel would be at the same distance from the center of the wheel at the origin, and we can specify the location with just one number, which is the angle that that particular point is from some reference line. In this third picture, we have Wile E. Coyote with his very creative ice-making, snow-making machine so that he can ski down a hill. And when we see problems like this, we will frequently choose a tilted coordinate system, because then his motion can be described as totally being in just the x direction. And this we'll find will simplify problems like this. So the important thing to keep in mind with a coordinate system is that whenever we have a problem, we'll need to choose a coordinate system. We'll have to choose an origin and then some axes or a system of coordinates that makes the problem as easy as possible. So let's take a look at this example, and this example involves changing between one coordinate system and another. So we have here a point in radial coordinates. It's 5 centimeters from the origin and at an angle of 32 degrees from our reference line. We want to change this into x and y coordinates, where we assume that the reference line is the x-axis and the line 90 degrees to that is the y-axis. So let's take a look at this problem. So first I'll redraw the problem. I'll redraw the point in radial coordinates. So we have our x and our y axes, and the point is 5 centimeters from the origin. So let's say this is our point. It is a distance of 5 centimeters from the origin. And we want to know what are its x and y coordinates. How far is this point in both the x direction and in the y direction? Now I can make this a little bit simpler if I drop a line directly down from the point to the x-axis. I know this angle is 32 degrees, And so now I have a triangle that I can use some trigonometry with in order to find these distances or these coordinates in the x and y coordinate system. So first off, let's consider the sine of this 32-degree angle. So the sine of an angle is, if we have a right triangle, the opposite over the hypotenuse, and in this case the opposite side is the length of this triangle, which is the same as the y-coordinate of my point, and the hypotenuse is 5 centimeters. So I would write down that the sine of 32 degrees is equal to y over 5 centimeters. So that means that my y-coordinate would be equal to 5 centimeters times the sine of 32 degrees, which means my y-coordinate would be 2.65 centimeters. So you should try plugging that into your calculator to make sure you get that same result. If you don't, it may be that your calculator is in radian mode instead of degree mode. Okay, so we've now found the y component, or the y-coordinate. Let's look at the x-coordinate. I think I can get that by considering the cosine of that 32-degree angle. So the cosine of 32 degrees would be adjacent, which is the x-coordinate, or the length of the bottom of my triangle, divided by the hypotenuse, which is 5 centimeters. So to calculate my x-coordinate, I would take 5 centimeters times the cosine of 32 degrees, which gives me a result of about 4.24 centimeters. So now I can write my point in the xy coordinate system. So the xy coordinates of this point would be 4.24 for the x and 2.65 for the y direction, and that would be in centimeters. So the next thing we want to discuss is a physics concept called path length. The path length is the distance covered by a moving object, and we use the symbol s to represent path length. S is a function of time, and it changes as time goes along. So we see in this picture a ball, and we can see that the path length would be the length along the path that the ball travels. Another important concept is speed, and speed is a measurement of how fast an object is moving along its path. We break this down further into two types of speed. There is an average speed, which is the speed averaged over the entire trip. So to calculate average speed, and you can see we use a bar here over the v to designate average, the average speed is the total path length, the total distance along the path that the object traveled, divided by the total amount of time it took to move along that distance. On the other hand, we have instantaneous speed, which would be the speed at any instant in time. So something like a speedometer reading. You could be moving at very different instantaneous speeds. They could be either greater or lesser than the average speed for your whole trip. So for example, if you took a trip and for part of the trip you were going along a country road, your instantaneous speed at that point would be smaller than when you're on the highway. There your instantaneous speed would be much higher. So the instantaneous speed, you should think of a speedometer reading. The official definition of instantaneous speed is given by this equation. And this equation contains sort of a calculus idea. We won't be using this equation for doing calculations, but it captures more of an idea, and that is when you are finding an instantaneous speed, you're finding the speed when the time interval is very small. So with average speed, you could be averaging over a very long period of time. For instantaneous speed, you want to consider your speed at any instant, so over a very, very, very short time interval. And that's what's meant by this. We're taking the limit as the time interval is becoming very, very small. So for instantaneous speed, your speed at any instant, you would want to use a very small time interval to calculate speed. So let's look at this example problem of a family going on a road trip. So during this road trip, a family travels for half an hour to the highway, which is 22 miles from their house. They travel 136 miles in 2 hours. They stop for lunch for an hour, and then they reach their destination 3 hours and 201 miles later after they stop for lunch. What is the average speed during their trip? All right, so if we want to do this calculation, we need to remember that average speed is equal to the total distance traveled divided by the total amount of time it took to accomplish the trip. So if we look at the distances traveled by this family, they first travel for half an hour, which is 22 miles from their house. So first they go 22 miles. Then they travel 136 miles in 2 hours. So we'd have to add to that the 136 miles. They stop for lunch. Well, they're not moving while they're stopped. And then they reach their destination 201 miles later. So the sum of those quantities would be how far they traveled, their total path length. Then we need to divide all of that by the amount of time it took to accomplish this journey. So first they traveled for half an hour. So 0.5 hours. Then they traveled for 2 hours. Then they took a 1 hour stop for lunch. That gets included too. And then finally they traveled for an additional 3 hours. So their average speed, adding all these things together, would be 55 miles per hour. Now at any point in their journey, their instantaneous speed may either be much faster or much lower than this. When they're stopped for lunch, obviously their instantaneous speed is 0. Okay, so these are the big ideas that we have looked at in this video. We've looked at coordinate systems and how it is important for problem solving to choose the most convenient for your problem. We've looked at the concept of path length, which is the distance along an object's path, and we've looked at 2 different kinds of speed. The average speed, which is the entire path length divided by the entire time for a trip, and then also the instantaneous speed, which would be something like a speedometer reading. So this concludes the material that we've covered in the first day of summer general physics.